Hello again, this is Daniel Pickett, Cal State Long Beach. I want to talk today, this is Physics 151 again, today about the multi-particle momentum principle and what happens when there are no important forces coming from outside the system. This is the case of collisions, so 3.13 is what we're talking about today. And here's a scenario that I want you to think about. And we'll talk about this in online office hours, but I've got a situation where I've got a car of mass m approaching, a car of mass m approaching an intersection traveling with speed v0. And I've got a car or say a truck with twice the mass going the same speed. So both these objects are obeying the speed limit, but there is a problem with the stop sign. They collide and they slide off with some final velocity in the direction that I've shown. Now that's one situation. Compare it to, again, the initial car is going with a velocity v0, but now I've got a car coming from the south, same mass as the initial car, but a speed which is twice as big. Now both of these two situations have got exactly the same total momentum of the system in them. So if I look at what is the momentum of the system before the collision, so I've got two objects in the system, I add the two momenta together, that has got to be the same as the momentum of the system after the collision. And the same thing has to happen here as here. So for both of these, I can read off, let's say this is the x direction, that's the y direction. The momentum of the system, in this case, before the collision in the initial state, is m v0 x hat, that's this guy's momentum, plus the momentum of the truck going upwards, 2m times v0 times y hat. So the momentum of the system, I could also write it, and then just add those two things together as vectors. I could write it as m v0, comma 2m v0, comma 0. So that's the momentum of the system before the collision. After the collision, it's got to be the same. The momentum of the system final is equal to the same thing. That's the momentum principle, because there is no impulse from the surroundings. M v0, 2m v0, comma 0, because p system final is equal to p system initial plus delta t times the force from the surroundings, the net force from the surroundings. In this case, there is no force from the surroundings. It's the two forces between the cars are the only thing that's going on. This is happening, say, on a frictionless surface. So I get that the final momentum is equal to the initial momentum. Those two things are equal because of the momentum principle. Same thing happens over here. The momentum of the system before the collision is equal to m times v0, that is this guy's momentum, 0, comma 0, plus this guy's momentum would be, I have a mass m times a speed of 2v0. Oh, I gotta get this correct. I'm doing this in vector coordinates, so the x component here is 0, it's going straight upwards. The y component is the mass times 2v0, and then 0. And I add those two things together as vectors, I get m v0, 2m v0, and 0. And that is because of the momentum principle again. The final system momentum is equal to the initial system momentum plus delta t times f net. Well, in a collision, the f net is the f net times the delta d is negligible, so the initial momentum is the final momentum, so I get m times v0, 2m v0, comma 0. So in the final state, the wreck here and the wreck here both has the same momentum. The thing we'll talk about in online office hours is which one is going faster. Which of these wrecks, so here is v final for case A, here is v final for case B, which wreck is going faster? It has got to have the same momentum. Maybe it has the same velocities, but think about how momentum and velocity are related. It's related by the total mass of the system. Is the mass of the system the same in both of these cases? That's the thing that we'll be talking about.